So we're now in chapter 2. We're talking about atoms, molecules, and ions. We're not really going to get in a lot to the periodic table today. We'll get into that in the next uh, following chapter. We'll touch on it today, but we're not going to get deep into it today. But we will see it today. So we need to really understand atoms, how atoms were came to be and understood, molecules, ions, and it first started with Dalton's atomic theory. So Dalton had several theories, and we're just kind of go over those to understand uh, how our current theories now of atoms, molecules, and ions came to be. So his first one. So let's say this. So we have Dalton's atomic theory. So the first one was that matter is composed of atoms, right? So matter is composed of atoms, right? And atoms is what's considered the smallest unit of of any element, right? So the smallest unit of any element, right? And that's what we consider the atom to be. We're not talking about subatomic particles. We're not talking about electrons, protons, quarks. We're not talking, we're talking strictly the smallest unit of just an element, and that happens to be what we call the atom. So when we're talking about atoms, elements consist of only one type of atom, right? So if I have um, gold, all of the atoms that make up that gold are gold atoms, right? I don't have silver atoms in there. I don't have copper atoms in there. I don't have zinc atoms in there. I don't have hydrogen atoms in there. If I have uh, gold in my hand, all of the atoms in there are the same, right? They're of one type and they're only gold atoms, right? So number two, we'll put that down as that elements consist of only one type of atom, right? And the characteristics of the element are the same for each atom, right? Electrical conductivity, melting point, boiling point, all the characteristics, all the physical and chemical characteristics all the physical and characteristics of an element are the same for each atom, right? Uh, they all, it's not like one atom melts at a higher temperature than another atom, is that they all begin to melt, boil at the same temperature, right? So all these chemical and physical characteristics for every element are the same for every single atom. Let's see, number three. So atoms of an element differ in properties of other elements, right? So let's write this down. I'll kind of describe that. So atoms of an element differ in properties. Man, my chicken scratch. You guys are gonna be experts by the time end of the semester. Properties of other elements, right? Atoms of an element, different properties of another element, right? So the atoms of gas, of hydrogen gas, so the atoms of hydrogen gas are different than atoms of copper. right? The atoms of chlorine are different than the atoms of iron, right? So they all differ in these different properties. Let's see, number 4 is that compounds consist of atoms of 2 or more elements in a whole number ratio. And the number of atoms is always the same, right? The number of atoms are always the same, and they're always a whole number ratio when we're talking about the compounds. And I'll show you what that's. I'll show you what I mean by that. But let's get this definition down. So compounds consist of atoms of two or more elements in a whole number ratio, right? And the number of atoms is always the same. Always the same, right? At this whole number ratio, and that they're always the same, right? Well, how can this be explained? All right, well, so everybody knows what water, I think almost everybody knows, right? Is that water is H2O, right? This is not water. H and half an oxygen, right? Uh, is that here, just because we simply divide it by 2 and go, well, we got 1 atom of hydrogen and half an atom of oxygen. No, all of these compounds exist in a whole number ratio. They all exist in a whole number ratio. And the atoms are always the same. Hey, let me cross that out. We don't want that. That's no good. And the number of atoms is always the same. H2O is what makes water, right? Just because I add another oxygen, well, I do have at least 1 oxygen, and I do have my 2 hydrogens, that this is not water. Water always has the same number of atoms. Water is always H2O, right? Here we have this 2-to-1 ratio, and here we have a 2-to-1 ratio, right? Here we have a 2-to-2 ratio, right? That is not water. H2O2, if you're curious, is hydrogen peroxide. All right. Now, atoms, just like energy, we have a law of thermodynamics. We can't create or destroy energy. Well, we have the same thing with Dalton's theories, is that atoms are neither created or destroyed, right? So number 5 says that atoms are neither created or destroyed, right? During a chemical change, we can make them into a different substance, right? Uh, but we can't just create atoms out of thin air, and we just can't destroy them and have them disappear. And I'll give you just kind of a small example of what I mean by that. So I'm going to give you a formula here, right? If we take hydrogen gas, and the small subscript, so when I write this is equal to gas. So I have it down as a subscript. So if we take some hydrogen gas and we add it to some oxygen gas, we get liquid, and this is a cursive L, so if you see me writing this, that equals liquid. Right. So here, if we take a look at this formula, we're not going to get too involved in the formula. We're just kind of trying to understand Dalton's laws here. or I'm sorry, not laws, but Dalton's atomic theories here. So uh, here we have, if we look at the reaction here, I have two atoms of hydrogen. And when I finish the reaction, I still have two atoms of hydrogen. Here I began with two atoms of oxygen, but interestingly enough, I only have one atom of oxygen, right? But this kind of violates his theory here, is that atoms can't be destroyed or created. So there is a way to fix that, and we're not going to really get into this today. Okay, um, but we use what's called coefficients, and if I put this 2 in front of here, well, this 2 gets distributed here, and it gets distributed here, which means now I have my two atoms of oxygen, but I also have four atoms of hydrogen, but I'm going to put that same 2 over here. So now we can actually see here, I have four atoms of hydrogen, two atoms of oxygen, four atoms of hydrogen, two atoms of oxygen, and we didn't break his theory here, is that we didn't destroy any atoms and we didn't create any atoms. So again, balancing equations is something we'll get into in a later chapter. This is just kind of a basic reaction to help you understand one of Dalton's theories here regarding atoms and not being destroyed or created. Let's see. No, no number 6. So let's take a look at what we call the law of definite. Let me see something here. Go. Oh, there it is. All right, we're good. I just didn't have the chat up. I was trying to find it. All right, so the law of definite proportions. Some also call it the law of constant composition. All right. So what we mean by this is that pure compounds pure compounds. We're not talking about mixtures here. We're not talking about homogeneous mixtures. We're not talking about heterogeneous mixtures. We're talking about pure compounds here. So pure compounds contain the same elements in the same proportion by mass. The same proportion by mass. So this is isooctane. Isooctane looks like this. So this is what isooctane looks like. And isooctane has a proportion uh, of 5.3 to 1. 5.3 to 1. And it doesn't matter how much of it I have. Let's take a look at the textbook here. There's some values in here we can use. So just kind of as an example. Right? The law of constant composition, the law of definite proportions. And if you were to take samples of isooctane and measure out the carbon and measure out the hydrogen, is that they always, it doesn't matter what the total mass is, right? Is that when we break it down into individual masses, is that we're always going to end up with some 5-to-3 ratio, 5.3 grams of carbon for every 1 gram of hydrogen. And we can see that just kind of in this sample size here of measuring that out, is that when we break it down into masses of each element, is that the mass ratio is always the same. The mass ratio is always going to be the same. So we also have what's called the law of multiple proportions. The law of multiple proportions states that when two elements react to form more than one compound, right, is that a fixed mass of one of the elements, sorry about that, my mic went out there, is that you're going to have some fixed mass of one of the elements is going to react with one of the other compounds in whole numbers. In whole numbers. So it's better if we just take a look at an image in the book for this. Hold on one second. All right. All right, so the law of multiple proportions. So when two elements react to form more than one compound, a fixed mass of one element will react with masses of the other element in a whole number ratio, right? So we see we have two different compounds here. Two different compounds, but both of these compounds both contain chlorine and both contain copper, right? And they're both a 2-to-1 ratio as far as the atoms are concerned, right? But the mass ratio is going to be different here. The mass ratio of these, so the law of multiplication, so when two elements react, let's finish this definition. So when two elements react to form more than one compound, a fixed mass of one element, a fixed mass of one element will react with masses masses of another element. Let's put of other elements in whole numbers. So let's see how this actually works here. So we have chlorine and copper, right? Chlorine and copper. So we have this green compound versus this brown compound. Well, the mass ratio on those, for the green compound, the mass ratio is 0.558 to 1. And the brown one is 1.116 to 1. And this is chlorine copper. So here, this is chlorine and this is copper, and this is chlorine. Oh, chlorine, and this is copper. All right. So what do we mean by this law of multiple proportions here? All right. Well, these are definitely not whole numbers, but when we're talking about whole numbers, we're talking about the atoms, right? We're talking about Dalton's law here that we just went over, right? Is that they're always going to be in some whole number ratio. So if we look at these masses here, well, let's see if we can get this whole number ratio from these mass ratios. So if we were to take 0.558 grams of chlorine for every 1 gram of copper, and we divide that by 1.116 grams of chlorine for every 1 gram of copper. Can somebody give me the answer to that question? I got 24 students in here. I should have 24 calculators, so you guys need to calculate this and give me the answer.
It's 0.5 or 1/2.
Oh, you know what? I think I should have flipped these values around. Let me rewrite this. One point and 0.558. Now what is it? Sorry about that.
1.989.
All right, which gives us a, was that 0.558 or 0.588? It should have come out to a whole
0.5.
I got 2.
2. Okay, yeah, that's what okay, yeah, I was looking for the exact number 2. So we end up with this 2. So that gives us a 2-to-1 ratio, right? And there's our whole number ratio, right? And this comes from, again, Dalton's law supporting our law of multiple proportions. Let's take a look at it. Let's keep going with this topic here. They do have an example for you guys. So if we take a look at some compound, doesn't matter what the compound is, we'll just say compound A, compound B, and compound C. So I have 3 different compounds, and I will give you 3 different masses here. So we'll say the first compound was 2.28 grams of carbon and 0.19 grams of hydrogen. And compound B, when we weighed it, was 1.62 grams of carbon and 0.27 grams of hydrogen. And we got 5.16 grams of carbon and 0.43 grams of hydrogen. So now if we take a look at these, well, let's take the mass ratio of these. Let's take the mass ratio and let's do this math here. Let's go 2.28 over 0.19. And then we'll do 1.62 over 0.27, and then we'll do 5.16 over 0.43. And what answers do we get from these? So the first one?
Compound A is 12.
Okay, so we have, and this gives us a 12-to-1 ratio. All right, because, and again, I'm looking at it like this. If I see 12, I can go 12 over 1. So that's where I get that 12-to-1 ratio. All right, so we have 12-to-1, and the next one?
6.
So we have 6-1 and the last one.
12.
12.
So 12-1. So if we were to look at this, and we can actually say that you know what? Compound A and compound C are both a 12-1 ratio of carbon and hydrogen, that this is the same element. I'm sorry, this is the same compound. Whatever this compound is, they're the same. They both have a 12-1 ratio, and it doesn't really matter how much of it I had. So this supports the law of definite proportions, is that these pure compounds contain the same elements in the same proportion by mass, is they both come out to this 12-1 ratio. So we can say A and C support the law of definite proportions. All right. Well, let's take a look at this again now. Because I have these masses here, why don't we take one mass and divide it by the other mass? So we can also look at it this way. We can say 2.2, oops, 2.28 grams of carbon over 0.19 grams of hydrogen, and divide that by, let's say, 1.62 grams of carbon over 0.27 grams of hydrogen. And what answer do we get there?
Two.
2.
2, right? So we get this 2-1 ratio, all right? And then if we take a look at a couple more, how about we take a look at, we'll say 5.16 or 3, and we divide that by 1.62 over 0.27, and what answer do we get there?
Again.
And we get 2 again. We get this 2-1 ratio. So, right, when two elements react to form more than one compound, these fixed masses, right? These fixed masses are going to form other elements in whole number ratios. This supports, right, Dalton, or this supports like the law of multiple proportions, is that we have these masses that react that meet in whole numbers. And there's our whole number ratio there. So this, we'll say that A and B, and we'll say B and what's it? B and C, right? Support the law of multiple proportions. Okay, so I think moving on from here, I do need to show you an image of an experiment. So moving into how this atomic theory evolved, right, is that we'll start with this here. So this is the actual cathode. This is what we call a cathode ray tube, and all of the oxygen, all of the air is vacuumed out of this. So this is kind of a diagram of that there. And what Thomson did here is Thomson created a beam between two electrodes, right? So we have these two electrodes here, the cathode and the anode, and there was some electrical charge put between those two, and he was able to create this beam, right? This cathode ray, this beam that hit the other side, right? So in order to understand what was going on with this beam, what they did was they also, in this tube, they added these magnetic plates, right? So magnetic plates, like magnets, they have some, we're talking polarity, they have this positive charge, North Pole, South Pole, like we do with magnets, right? And something interesting happened when they turned on these magnetic plates, is that instead of the beam hitting directly across, this beam was now bent and it hit up here. So their observations led them to believe, because of this, they knew that when you put with magnets, and anybody that's played with magnets knows that if you put two of the positive poles together, that they repel. Right? And if you put the opposite ones together, then they attract. It doesn't matter positive, positive, negative, negative, is that when two poles of the same charge are together, they're going to repel. So this beam of light contained what they called electrons, right? And they discovered by their observations that the charge on an electron must be negative. Because if we look at this plate here, the reason why it's bending up is they know the charge on the plate. The top plate is has a positive pole, and the bottom plate has this negative pole. Well, if electrons are positively charged, well, the light would bend downward toward the negative pole there, but it didn't. It bent up towards the positive pole, and this discovery was like, okay, well, this means that electrons here in this beam of light, electrons are negatively charged. So they coined this term. He coins this term electron. Right? So an electron is this subatomic particle that is negatively charged. Negatively charged. All right. So they knew that the electrons were negatively charged, and they know that atoms contain electrons. They know that atoms contain a positively charged particle, subatomic particle that we consider protons. So in order to actually figure out the charge, the electric charge on an electron, is that Millikan came up with this experiment here. So he put in this mist of water droplets, right? And he's watching those, and he's charging these plates up, and he's throwing on this X-ray. And what they found out is that they were not every drop was the same size, right? All these drops were different sizes, but there was one constant with these. When they were determining the charge of each one of these drops, the one constant is that every single drop was a multiple of this charge. Every charge on every single drop was a multiple of 1.6 times 10 to the minus 19 coulombs, right? It was maybe 3 times that size. So it was 3 times 1.6 times 10 to the minus 19, and that's 4.8 times 10 to the minus 19, right? Here it is, 4 times the size, twice the size, but everything was always some multiple of 1.6 times 10 to the minus 19. So Millikan's experiment determined that these droplets were always some multiple of 1.6 times 10 to the minus 19 coulombs. And that this must be the charge of an electron. And my shorthand for I don't always write electron out. My shorthand for electron is simply this, E with the negative symbol there. So this is equal to 1.6 times 10 to the minus 19 coulombs. Okay. So based on the research of Millikan and based on the research on Thomson's research, they were actually able to come out with the mass, because again, the mass to charge ratio. So this is what we call the charge to mass ratio of an electron. Excuse me, based on Thomson's research here. So based on his research was 1.759 times 10 to the 11 coulombs per kilogram. So this was enough information for them to calculate, because you can't actually pull an electron off and weigh one electron, is that they can mathematically calculate the mass of an electron now. Is that if they take the charge of an electron, 1.6 times 10 to the minus 19 coulombs, and they multiply that by the charge to mass ratio of an electron, and you know what, we can do this, right? We're chemists, we get to do a lot of stuff, and one of the things we can do is we can use reciprocal values any time we feel like. Remember that. You're a chemist, anytime you want to use the reciprocal of something because you need the units to cancel out, be my guest and use the reciprocal value. It's our right as chemists, and this is what we get to do. All right. So if I use the reciprocal value here and put 1 kilogram over 1.759 times 10 to the 11 coulombs, well, these units cancel out, and I end up with a mass of 9.107 times 10 to the minus 31 kilograms as the mass of an electron. Right. So again, remember that if the units don't work out the way that you're looking at it, flip it around and make sure you guys are cross canceling there. All right. So we start, evolving, right? We start learning massive electrons, massive protons. What does an actual atom look like? So the original thought to an atom was what we call the plum pudding model. Excuse me. So our plum pudding model was just like, I don't know if anybody's ever eaten plum pudding. I sure haven't ever eaten plum pudding. But that it was filled with electrons and protons just everywhere, right? So I think your book shows a picture of plum pudding here. So this was kind of the original thought of what an atom looked like. Is we had this mass here, this matter, and in there we shove in these protons and electrons that are just kind of arranged around. But then it was thought more to look like this. Isn't the final model, but then they start thinking that, well, maybe we have this positively charged matter on the inside that we call some nucleus, and on the outside of that we have some electrons. So that was kind of the other one that was going around, is that here we have this nucleus, and we have some protons in there, and the outside of that, right? This is where our electrons must be sitting is way out here. And that kind of led to the discovery that, you know what, that atoms really have a lot of empty space. There's a lot of empty space in an atom. And they use an analogy of a football stadium, that if you can imagine a professional football stadium, and that's the size of your atom, right? That the nucleus here would be about the size of a blueberry, right? So there's really a lot of empty space with the electrons surrounding that nucleus, right? There's just a lot of empty space there. So now we try and start determining masses of protons, masses, charges, and what developed was something we call the atomic mass unit, and we'll do AMU for short, right? And this was all based on what we call carbon 12. Carbon 12 is an isotope. And we'll get into isotopes today. We definitely will, but just know that this was based on carbon 12, which is just an isotope of carbon. The simple answer for isotopes is that isotopes have a different number of what we call neutrons in the nucleus, right? And we'll definitely get into isotopes today. So 1 AMU was equal to 1/12 of carbon 12. That's not carbon minus 12. It's just labeled carbon 12. That's what we call it. So it's not 1/12 times carbon minus 12. That's not what we're looking at here. 1 AMU is just equal to 1/12 of the isotope carbon 12. All right. And comparing it to grams, 1 AMU is equal to 1.6605 times 10 to the minus 24 grams. And this is what an AMU weighs in grams. Okay, so protons, and I use this shorthand for protons. That's my shorthand for protons. So 1 proton is equal to 1.0073 AMU, right? And it's going to have a charge associated with that. So electrons are negatively charged and protons are positively charged. So I'll say of 1 plus. So protons weigh 1.0073 atomic mass units, and they have a charge associated with that of 1, a positive charge. Now electrons, and again, I'll give you my shorthand there. So 1 electron, 1 electron is equal to 0.00055 AMU. Not even close to what a proton weighs, right? And we know that its charge has a charge of 1 minus. So protons are positively charged, electrons are negatively charged, and then we have neutrons. And this is my shorthand for neutron. So 1 neutron weighs 1.00, just slightly heavier than a proton, AMU, and there is no charge associated with a neutron. But as far as AMU is concerned here, is that we see that 1 proton is almost the same mass as 1 neutron. Right? And that's what we should take away from this. And also that an electron is not just less than a proton and neutron, but it is a lot less. So this is means a lot less, right? So this is a lot less than a proton. So when it comes to the mass of an atom, the mass of an atom, we only consider the mass of protons and neutrons. It would actually take about 1,800 electrons to weigh the mass of one proton. And the heaviest element out there has 118 electrons. Or oganesson or something to that effect. I don't even know the last one. But that's a maximum of 118 electrons, right? So we don't ever consider the mass of an electron when we're talking about the mass of an atom. So the number of protons, so the number of protons in the nucleus, the number of protons in the nucleus is also its atomic number. Is also its atomic number, right? And we use a symbol of Z for this. So Z represents the atomic number, right? I mean, yeah. So when we look at a periodic table, right, we have, oh, come on. Where'd it go? Where'd it go? There it is. We look at a periodic table. We're not going to get too involved in the periodic table, but again, like I said, I would introduce it. We'll get more into it next. Might cut off. I have this wireless headset, and it just kind of cuts off after I've been talking, or it just kind of cuts out. It only happens when I lecture. Like it doesn't happen when I'm gaming or if I'm watching a movie or something or Twitch. It doesn't happen. Just when I'm lecturing for whatever reason, I don't know. It cuts off about after a half an hour, 45 minutes. Okay, so back to what I was saying here. The number that you see on top. So here we see hydrogen has a number 1 on top. That's its atomic number. Right? The atomic number was not given in order of discovery. Like I've had students go, oh, that's when they discovered it, or hydrogen was the first one. No, that's not the case. It's not in order of when they found it. The atomic number is how many protons that particular element has. So hydrogen has 1 proton. Iron, number 26 here, Fe is iron. Iron has 26 protons. Gold, which is Au, has 79 protons. And you'll notice that every single element on the periodic table has its own unique atomic number. There's no 2 atomic numbers that are the same. They are each having their own unique atomic number because that's how many protons they have. If I have an element with 27 protons, well, it's not iron, it's cobalt. If I have an element with 25 protons, well, it's not iron, it's manganese. I need 26 protons in order to be considered iron. So the atomic number, and again, I'm going to put Z here, is equal to the number of protons. Now, the mass of an atom, and we're going to use this symbol A for mass of an atom. This is equal to the number of protons plus the number of neutrons. And there is going to be some rounding here. Like we'll take a look at it, but let's see. We see all these individual masses. So the values that are on the bottom, those are the masses. So iron weighs 55.845 atomic mass units. Uh, Potassium, K, weighs 39.0983 atomic mass units. Has 19 protons and weighs 39.0983 atomic mass units. And how we get that is that if we take A, the mass, and subtract Z, the atomic number, this is equal to the number of neutrons. If we just subtract those two values, we get the number of neutrons. And everything on the periodic table is considered to be neutral, that there is no charge on these elements, right? If we know that neutrons don't have any charge, but protons have a 1 plus charge, electrons have a 1 minus charge, and if I want them to be neutral, I have to have the same number of protons and the same number of electrons, which means that if iron, atomic number 26, means there's 26 protons, it also means there are 26 electrons. Lead is Pb, atomic number 82, has 82 protons, but that also means it has 82 electrons. So the number of protons is equal to the number of electrons, right? So let's kind of take a look at some of the items that we have here. So I'm going to write this generic version here, and we'll say X, A, and Z. This is going to represent the element. This represents the atomic mass, and this represents the atomic number. And we know the atomic number is equal to the number of protons. And we know the mass is equal to the number of protons and the number of neutrons. So if we had an element that looked like this, and A, and I put, we do have to round these numbers. I'm going to put 23 and 11, but this is where I get those numbers from. Na is 22.989769. But remember that protons don't weigh exactly 1 AMU. They weigh 1.0073. Neutrons weigh 1.0087, right? So these values here, right? Like iron is, I'm going to round it to 56. Ruthenium, I would round to 101. Molybdenum, I'd round to 96. Potassium, I would round to 39. Right? So there is some rounding involved when we're going to determine the number of neutrons here. The number of neutrons, again, in order to figure out the number of neutrons, we take the mass and subtract the number of protons. So the number of protons here is 11. The number of electrons is 11. And the number of neutrons is A minus Z. The mass, which equals the mass, 23, minus the number of protons, which equals 12. So the number of neutrons is equal to 12. Right. If I wanted to do that with iron, let's do it with iron. Iron has an atomic number of 26. Atomic number of 26. And it has a mass of 56. It says 55.845, but I'm going to round it to 56. Well, the number of protons is equal to 26. The number of electrons is equal to 26. And the number of neutrons is equal to the mass, 56, minus 26, 30. Let's do iridium. Iridium is 192 and 77. And I know that because I used to work with iridium quite a bit, which means protons, 77, electrons, 77, and the number of neutrons, 192 minus 77, 115 neutrons. Okay. So when we're looking at these protons, so we can't change the number of protons in an element. If I change the number of protons, we change the element, right? So we never change the number of protons, but we can change the number of electrons, and we can have a different number of neutrons, right? The number of neutrons can change in an element, and it's still going to be, if I don't have 30 neutrons in iron, I still can have iron. I can have 29 neutrons and still have iron. I can have 31 neutrons and still have iron as long as I have 26 protons, right? I can have 24 electrons. I can have 23 electrons. I can, and I still have iron as long as I didn't change the number of protons. So changing the number of electrons, right? These are what we're going to call ions. So ions are atoms that have what we call have an electrical charge. So ions are atoms that have an electrical charge. So we can take a look at, say, this is sodium. Sodium is atomic number 11, which means that it has 11 protons and it has 11 electrons. Now, we know the charges associated with those are positive and negative. So we know that one positive charge cancels out one negative charge. And here, there is no overall charge. But if we happen to take away an electron, and let's say we have 11 protons still because it is sodium, but now we only have 10 electrons. Well, we can see here that since protons are positively charged, I have more positive charge. And the difference between the 10 and 11 tells me how much of a positive charge difference there is. I'm positively charged by 1. And we represent that up here. And we'll write 1 plus, not plus 1. We write 1 plus. So you can either write it like this or you can write it like this. It means the exact same thing. Oh, excuse me. Hold on a second. Oh, that was a bad attack there. All right. Let's take a look at another element here. How about we look at iron? So iron is atomic number 26, which means it has 26 protons, 26 electrons. But if iron happens to give away a couple of electrons, let's see what happens. 26 protons, but we give 2 away. We're going to have 24, and we'll give away the give away and accepting. We'll cover that in another chapter, the chapter 3. This is just kind of an understanding of ions here. Is that we now see there's a charge difference here, right? That I have 2 more protons than I do electrons, and that's giving me a positive charge there of 2 plus. And we represent that up here, we go 2 plus, right? If we use iron again, right, and we say we have 26 protons and maybe we have 23 electrons, right? That's a difference of 3 positive charges, and we represent that up here. We would say that that's 3 plus. So we
So
can
since
look at,
the protons are tied to the element, it can only ever be more or less electrons.
yeah, it can only ever be more or less electrons or more or less neutrons, but never more or less protons. If we take away a proton from iron, we don't have iron anymore because the number of protons are directly tied to each atomic number, which means if I have one less proton, we have a different atomic number, which means we have a different element. Does that make sense?
Yeah.
Yep, good question. Thank you. Um, so we've taken away electrons. Well, how about we give electrons away? So, or give electrons out. So let's say we have oxygen, and oxygen, atomic mass of 16, 8 protons. We have 8 protons, which means we have 8 electrons. But let's say oxygen gains 2 electrons. So we still have our 8 protons, but now we have 10 electrons, which means that we have more negatively charged particles on this atom now. And the difference there is a negative 2, 2 negative. And we represent that up here. Let me put that in a different color to keep track of it. It will say that that's 2 minus. We can do the same thing with chlorine. How about we do chlorine? So chlorine is atomic number 17. So I have 17 protons, 17 electrons, and let's say chlorine takes 1 extra electron. Right? There's a difference of just 1 electron now, and we're going to represent that here as 1 negative. Or if you wanted to write it, you could write it like this as well. They're both the same answer. So any ion that's positively charged, so a positively charged ion is a cation ion, right? A negatively charged ion is an anion. So you aren't going to, this, and these are the terms that you're going to hear me say. So when we're talking about these, I'm going to say cation, I'm going to say anion. I'm not going to say negatively charged, positive. I'm just going to say cation, anion. And those are the terms that I'm going to be using. I guess we could do one more. So what if we had something like this? I'm going to do one more quick example, and then I think we're going to keep going. I can, yeah, we'll get into isotopes. Let's say we had how about All right, so let's take a look at zinc. So zinc is 30 and has an atomic mass of 65. Zinc 5 is 30, and I'm also going to do this. So now we're going to need to determine the number of protons, electrons, neutrons. So the number of protons, well, that's right here. I have 30 protons. The number of neutrons, well, I'm going to take the difference of the mass and the number of protons, and that's going to give me 35. Well, now I need to figure out the number of electrons, because notice here, this says 2 plus, which means I'm positively charged by 2, which means I have 2 more protons than I do electrons, which means the number of electrons is going to be 28. All right, so now I think we can move on to isotopes here. So isotopes vary in the number of neutrons. So I mentioned carbon-12 earlier. So carbon-12 is an isotope of carbon. So if we take a look at some isotopes here, here's a small list of isotopes your book gives you, but every single element has these. So every element has isotopes, right? So hydrogen, when we look at hydrogen, here is hydrogen, 1 proton, and it has an atomic mass of 1. But we also have hydrogen that has 2 protons. I'm sorry, not 2 protons. Hydrogen that has 1 proton and 1 neutron. A hydrogen that has 1 proton, 2 neutrons, giving us a different mass. As long as we don't change the protons, we can have a different number of neutrons. So every element has these. Some have 3, some have 2, some have 7. We'll see carbon-12 here. Carbon-12 has 6 protons, 6 neutrons. Carbon-13 has 6 protons, 7 neutrons. And then we see the mass of them. So here, if we look at carbon, carbon has a mass of 12, 13.0034, 14.0032, right? Nitrogen, 14.0031, 15.0011. And let's take a look at nitrogen, 14.0031, 15.001, and then let's take a look at this, where we find nitrogen at 14.0067. Carbon, 12.0107. But carbon up here, we have 3 different masses for that. So the masses that you see on the periodic table are what we call a weighted average. My throat is getting very dry here. So the periodic table has weighted averages. Weighted averages. So they take account of the averages, and that's what's put on there. So you guys know how to calculate averages. I'm assuming you guys know how to calculate averages. So if I had 1, 2, and 3, how would you guys calculate the average of that?
Add them all, divide by 3.
Add them all, divide by 3. So we get 6, divide by 3. This equals 2, right? Yeah, don't do that. That is not how we calculate a weighted average. weighted averages have to do with what we call percent abundance. Okay, so would I put something like that on the exam? I 100% absolutely would, right? Because I know students, I'm not trying to trick students, but that's definitely not how we calculate a weighted average. So if we take a look at this table, we see this column at the very end. It says percent of natural abundance. And if we take a look at lithium, right? Lithium 6 with 3 protons and 3 neutrons. Out of all of the lithium that exists on Earth, 3 protons and 3 neutrons is 7.59% of the lithium. Lithium that has 3 protons and 4 neutrons will naturally, out of all of the lithium on Earth, 92.41% is lithium 4. I'm sorry, lithium 7, right? So we have to take account in these natural abundances, and that's how we're going to calculate a weighted average. So let's do magnesium. So we're going to use magnesium 24, magnesium 25, and magnesium 26. And the mass of each one of those is 23.98, 25.98 AMU. So these are the masses of each one of these, each having a different number of different number of neutrons. And their abundance, their percent abundance is, this is 78.70%, 10.13%, and 11.17%. Now, in order to figure this out, we have to multiply these percentages and the AMU together. But the AMU is in decimal notation, not a percentage. So before we can even multiply this together, we don't multiply percentages and decimal notations together. We're always going to get a wrong answer. We have to convert the percentage into a decimal notation. Then we can multiply by the AMU, right? So we're going to convert this to 0.7870. How did I get that? I divide by 100. That's how you get out of a percent. Divide by 100. And here we're going to get 0.1013, 0.1117. And now we're going to take that AMU and multiply. 23.98. Left-handed 8s are horrible. Let's see, 24.99, 25.98. You guys have calculators, so go ahead and calculate those and provide me some answers.
So the first one is 18.87.
Keep going.
You want more decimals or
All of it.
226.
Okay, the next one.
2.531487.
And the last one.
2.901966.
All right, so now to get the weighted average, what we're going to do is, because we took the percent abundance into account, we're simply just going to add all of those together and add them, and we're going to be 2 past the decimal.
So 24.31.
24.31 AMU. And let's take a look at our periodic table. If we round this to 4 significant or 2 past the decimal, magnesium would be 24.31. So this is how we calculate a weighted average, or average. I think the book uses average atomic mass. I better write that down as well. Average atomic mass. All right. We're not going to be able to, we don't have enough time to calculate. When we come back, we are going to calculate percent abundance. That takes a lot more math understanding. There's some stuff we do, some manipulation with substituting, and we have to kind of be careful of that. I can't do that in 7 minutes. I wouldn't do you guys any justice. I would just blow right through it. So we'll talk about that when we get back on Monday. We might, I don't know, depending on how many samples I have, we're going to be doing a lot of calculations on Tuesday, so bring your calculators. I'm, if I only have one person answering questions, I'm just going to start calling on people. So have a calculator prepared, because we are going to be doing calculations, a lot of calculations on Tuesday. Be prepared for that. So make sure you have your calculator. And give me these answers when I ask for them. Okay. Other than that, I'm going to go ahead and stop this recording.